So I asked this first review question here. What are the failure modes of tension connections? What are the things that we check for? Block shear is one of them. What else? Yield. Fracture. Bolt shear. Bearing and tearing, right? Bearing and tearing. And we're going to be reviewing each one of these. If you have not seen one of these previously, then there will be some review on it, but you probably should study it pretty hard. There'll be example problems that I'll present on every one of these, but I will not spend time to cover them in class. We've already talked about yield, and we've already talked about fracture. So what is yielding? It's the point where your material starts to stretch without much additional load, right? Your material starts to stretch without much additional load. So is yielding really failure? Well, I'd be careful not to say no. All right? I mean, it depends what people's definition of failure are, okay? Yielding can be a big problem, and yielding can cause big issues. Just because something doesn't break in two does not mean that it did its job, all right? So, yeah, yielding is, I would call yielding failure. Okay? Gross yielding is what we're talking about. Yielding on the gross cross-section. That is failure, and that's not something we want to happen. So what area do we use for yielding, the yielding check? What's the equation? Phi Pn equals what? Ag Fy. Is that right? Am I missing something? Need a phi factor, right? What's the phi factor for yielding? 0.9. 0.9. 0.9 AgFy, and Ag is the yucky area, right? The gross area. What does that mean? Don't subtract holes, right? We don't subtract holes. We leave them in. But why? Because don't holes take area away? Why do we leave them in? Yielding's occurred away from these ends, right? If we have a connection with some holes in it, right? We're worried about yielding here, right? How about yielding here? Is that a concern? Only if it happens throughout the entire cross-section. Even then, we don't care about yielding because it's so small. We care about fracture, though, on that cross-section. Yeah. This is where fracture occurs. This is where yielding occurs. Looks like some freaky airplane. No, it's a steel connection, right? Okay. So what's fracture? Hey, that's just what we talked about. That's where the area usually occurs around where the holes are. With welds, that's not always the case, but it's the area near the welds, right? It's where everything on the cross-section reaches its ultimate strength. We do have to take out the area for the holes, right? Right? So what area do we use? We use the, what's it called? The net area, right? And then we'll talk about effective area today, because net area is a little bit different than effective area. Okay, so how do we handle fracture on a diagonal path? So what I mean is if I have a hole here and a hole here, and I'm pulling on it with P. We have something to do for diagonal. Let's make sure we all hit our little red buttons when we're going to talk so we can share our thoughts with cyberspace, right? Okay? So what do we do when we have a diagonal?
S squared over 4g.
We use S squared over 4g, okay? That's a great answer, but let's give it more details. Is the answer S squared over 4g? You have to do a little more than that, right? So how do you systematically work this problem to figure out what this fracture path would be? You would say phi Pn is equal to 0.75, and what's that? It's the fracture phi factor, right? Times my favorite variable Fu, right? And then what?
Net area
Plus the diagonal.
plus the diagonal.
Yeah, and I think the way we do it is you hit the red button, you hit the teleprompter button down, and you keep talking, and then you pull your finger up. That's how you talk to cyberspace, all right? Okay, so to do this, we would take the entire width, which we'll call B, okay? You would take B, you'd subtract out some holes, right? How many holes we got? 3, right, Jennifer? No. She's looking happy today. 2 holes. Diameter of the hole plus 1/8 of an inch, right? What else do I have to add? What I've done here, I've really gone straight across, right? I've gone straight across. I've acted like this is straight, right? So far, you with me? But that's not straight, is it? It's got a diagonal. That means we can take more capacity, right? It's not just purely a fracture. There's some shear going on simultaneously, right? The length is a little bit longer. We're not able to take the diagonal, though. What we do instead is we add to it this s squared over 4g term. Okay, where this is the s term, this is the g term. Okay, the spacing and the gauge of the holes. And then what do? Are we done? What am I missing? Thickness. Very good. Units. Units, units, units. Okay? Check your units. Every one of these problems. Okay? That's how you're going to work a problem like this, and I'm expecting you to know it backward and forward. There's example problems on your handouts about it. Any questions? Okay, well, one thing that we have done in the past here at OSU that I want to share with you, and that one thing that I'm planning on having your group do for the future, is that there are all kinds of these cool phenomena that we try to talk about in class, yet they were discovered back in the 50s and 60s, and there was no movies of it, right? Maybe a couple pictures, but no real movies, okay? And in this class, what I'm hoping for your class to work on is buckling of columns, okay? And we're actually going to produce some models so you can shoot videos of showing different buckling types, all right? And you're going to be designing the models, okay? And I'm hoping we're going to fabricate them, or we'll fabricate them this summer, depending on when we'll have time, all right? Okay, so why is this cool? Well, it's because, hey, we've been talking about these things. Why don't we look at, like, yielding, for example? This is 8 times the normal speed. Okay, we're showing the side view, the front view. This is supposed to be like a diagonal view. This is showing the middle of the member. We're pulling, we're pulling, we're pulling. And it just keeps going and going and going. Oh, baby, look at it go. Okay, that moved a lot. I can watch it again. And we can see that every one of these squares, when we watch it this time, thinks about half an inch. There's a half an inch per square. Okay? Half an inch per square. Or maybe a little less than that. Yeah, I think it's about half an inch per square. And we go, and we go, and we go. Oh, pause for me. Thank you. Look at that. That's way more than half an inch, isn't it? Look at that. That's more than half an inch. Okay? What's going on? It's getting longer. Look at this one. That's way more. It's getting longer. They're elongating. Okay? And if we notice when we watch this movie go, I'll show it again here. And if we talk about the rate of movement that occurs over this test, it's loading at the constant rate, and they're not really changing in size, are they? We're pushing constant rate. It's not really changing in size at all. Then all of a sudden, Oh, it's going faster. Oh, whoa. Okay, and that's what it would feel like as if you're riding on that structure, right? I'm doing good. It's elongating a little bit more, then, oh, Nelly! And like you feel like you're going to fall off the edge of the cliff. Okay? You with me? Okay, well, there's yielding. Okay, so let's look at some fracture. Okay, when we talk about fracture, again, it doesn't happen in the bulk of the member. Okay? Fracture happens at the end. This is at a bolt. This is cool. So again, this is front, this is side, this is the diagonal. Boom! Breaks. Let's watch it again. Oh, I forgot. Got to hit that one. Start going, and we watch the side. The side's kind of cool, and the diagonal's kind of cool, because what we can see is we start to see yielding. We start to see this kind of lift up. We'll pause it right here. See how that's kind of no longer the same length in that area? See how we see some necking? What does that mean? It's yielded, isn't it? But did it break? No, it didn't break. Okay? And actually, if you compare the elongation, it's not even very much. Look, these tick marks are about the same size all along the length. It's yielded locally, and who cares? You with me? Okay, we can keep going. Now that's a little troubling, right? That's a little troubling when you start to see that start to neck in. That's when you probably want to run, okay? If you see that in a real structure, all right? Okay, probably. Depends what the loading is like. Okay, if it's actively being loaded, I would run. Okay, and then as we start going, it necks further, right? See it necking further down. Okay, but again, we don't see a lot of movement here. Again, we see it, oh, baby, and it broke. Okay, now we were using hydraulics to load this. Okay, the cool thing about hydraulics is that when it breaks, it just lets go. Okay, it's not pushing. If this was gravity loads, what would happen? This would shoot off, right? It would fly. And that is failure. And that's what we'd like to avoid, at least failure for a fracture connection. You with me? That's what we'd like to avoid. Okay. Any questions on that? No? Okay. Before I forget, I sometimes haul these test specimens. I still have them. I sometimes haul them to class and hand them around. But you guys are too far to walk to, all right? In cyberspace, you are way too far to walk to get to you, all right? So come by my office, okay? And on my wall in my office, I have them all hanging up, all right? So you can come by and see them, okay? Great. Okay, let's talk about affecting that area now. In the previous calculations, we assumed that the stress is uniform. Well, it's P over A, right? Yeah. Not always, but we assume the stress is uniform at the net and the gross areas. This approximation is reasonable for sections away from connections and may or may not be reasonable or be accurate at connections. If a connecting member has an outstanding leg, then the stress will not be constant. I will underline this. If a connecting member has an outstanding leg, then the stress will not be constant. Okay? You should have a bell that goes off in your head. Okay? If you ever see a connection design with an outstanding leg, whoa, there may be shear lag, is what you should be saying to yourself. All right? Well, what is shear lag? Well, let's talk about what I'm saying here. I basically, if we have a connection that looks like this, an angle and an angle on the top, an angle on the bottom, and a plate in the middle hooked together by bolts, and I'm pulling with P here, and P over 2 and P over 2. And each angle is going to have what we call B, the outstanding leg, and A, the leg attached. You with me? Okay. So, stress must flow out of component B and into component A in order to reach the connectors. Plane sections do not remain plane near the connectors, and this is what we call shear lag. So if you have a hard time, if you're not quite understand what I'm saying out here the assumption of P over A is great and works just fine. And out here, the assumption of P over A works just great. But St. Venant's principle tells us anywhere we have connections or geometry changes, they don't work so well anymore. Okay? So what's going on? Well, the force has to flow. The force has to flow from this cross-section out. Okay, so let's think of it as water. Okay? Let's become the stress. Okay? Let's become the force, all right? Think about this we'll break this force up into 3 chunks, or chunklets of force, okay? We talk about the chunk of force at the bottom. It's running, think of it as water, it's going, and all of a sudden it sees 3 possibilities to leave the cross-section, okay? And this force is like an 18-year-old ready to get out of the house, or like, I'm out of here as soon as I possibly can, okay? So it's going to run through this bolt and go down at the bottom. You with me? Okay? This is one that comes down, and says, you know what? I like staying at home a little bit longer. I'm going to take my time leaving, and I'm kind of going to do some here, okay? And then we have the folks that say, you have to kick these kids out of the house. You know who I'm talking about, right? The ones at the top that come down and says, I don't want to leave, but there's no other way out but throughout the holes. You're with me? Okay. Throughout the holes. The cool thing is here is that there's no kids in the house, right? There's no stress at the backside, and that's what we're trying to figure out. That's what we're trying to understand and what we're trying to prove to people. You with me? The same thing is happening down here at the bottom. Goes and goes out, goes and goes out. Here, okay? And this is what I've tried to show here. I've tried to show the exact same thing. That what happens in every one of these connections is that here in this zone, and notice I don't have dimensions here. This is away from the connection. How far away? Well, a good number may be 2 times the depth, right? About 2 times the depth, or the depth. There really hasn't been a lot of work done on this, and if you were bored, you could do a bunch of finite element runs, and if you're rich and you're bored, you can do a bunch of finite element runs, but we're not going to worry about that as much, okay, for this class, all right? And it's about 2 times the depth is about where this becomes uniform, or 1 to 2 times. And in this zone, it is not uniform. And we see this same phenomenon showing that we talked about up here. And why we care about this is that if we were going to look at fracture, we would say fracture is going to happen here. How do I know that? Well, remember, I proved that before. I proved that if for a single number of bolts, there's going to be the most stress on this cross-section. If you don't remember, look back at your notes, all right? Okay? So it has to happen here. But now what I'm trying to communicate to you is this area isn't loaded. Well, that's not totally true. This area isn't loaded as high as this area. You with me? Okay? And it's the function of what the depth of the cross-section is, or really the distance between the centroid of the cross-section. That's why I call the center of gravity over here the centroid of the cross-section. It's really this distance from the centroid of the cross-section down to the bottom is one factor, and the other factor is the length of the connection. The longer the connection, the more area you're actually able to get into the act. Okay? The longer the connection. It means the distance from the first to the last. Okay? Doesn't matter what goes on in the middle. Okay? You with me? Okay. So we can see that since this is longer, once we force this stuff to flow and look on this cross-section, oh my gosh, almost all of it's in the effective area, right? We would assume we're going to calculate something called a U factor. Okay? We'd say our U factor is very, 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 very close to 1. A lot of times people like to use 0.9. They like to have this upper value on the U factor. Okay? It's actually required in the code. Okay? And then we have something like this, and the U factor may be closer to something like 0.6. Okay? What we're going to find out is this is a direct multiplier on our gross area, our net area, to make it our effective area. Okay, I don't spend a lot of time talking about this, but effective area is this U times A net. You know what? I think that's an equation I don't even really need to memorize, okay? Because I got too many other good things to put in my head, right? I mean, fantasy football starting coming up, right? I got to figure out what quarterbacks I'm going to put in, right? You know, I don't need to worry about this, but we realize that this may help you understand the trail of algebra, okay, that we are going to be using coming up. You with me? You know how to calculate this. We've already talked about it. Now you're just slapping the U in front of it. So there's more effective area in the long connection than the short connection. Welded connections behave the exact same way. There's that variable, there's that equation I just drew in there. And in this class, we're going to be using U is equal to 1 minus x bar over L. What's x bar? It is the distance from the connection to the centroid. Okay. What's L? It is the distance from the first connection to the last connection. Usually we go center to center of bolts. Okay? Well, how about welds? What do you do? What's that? Tell cyberspace.
Length of the weld.
The length of the weld, right? The very start of the weld to the very end of the weld, right? Well, what if I do something funky like weld all the way around? And this has an outstanding leg on it. This class is all about the funk, all right? What am I going to use for my L? All the way around? Does that make sense? Sure doesn't to me. Think about what's going on here. It's this distance that's important. It's this distance that's important. This distance, who cares? Right? Who cares? If that doesn't make sense to you, think about in this connection, if all of a sudden I put weld on the back, is that going to change what the stress looks like? Is that going to change what the stress looks like here? No. It doesn't. It sure doesn't. Now, what if I could find a way to put weld up here to connect it to something? Will that change the stress? Sure it will. Why? Because it gives it another path to escape. Right? Gives it another path to escape. What if I just put a bead of weld and there's no steel up there that it's hooked to? Does that help me? That's crazy, all right? That's crazy. But people do crazy stuff when they don't really understand what it is they're doing, all right? Don't really understand what it's all about. Because you have to have a load path, right? Got to have a load path. Okay, great. Now, we're going to use this equation, which hopefully everyone in this class has seen before. The other thing you can use, if you don't want to, is in your steel manual, you will find this table, and I've given you a reference to this table on a previous handout, and this is something you're going to want to have tabbed in your steel manual. And this is kind of cool. You can go in here and read and see if this pertains to your connection. You can go over here, and this is what it tells you what to use, and they have a couple pictures over here. I'm a big fan of 1 minus x bar over L. The cool thing is that with this U factor correction, is that you get to use the larger. So if the 1 minus x bar over L comes out to be like 0.7, and you look up in the table and you get 0.9, you can use 0.9. You say, well, how? That doesn't seem right. Well, if it freaks you out, feel free to use 0.7, okay? That's fine. But what's going on here is that there's a lot of assumptions that went into this, okay? There's a whole lot of assumptions that went into simplifying this extremely complicated transfer of load down to one equation or one value, okay? And sometimes, in certain circumstances, parts of the table are more effective than using the equation. What they've allowed you to do is use the one that's the least conservative of the assumptions. You with me? That's what they do. So we're going to use 1 minus x bar over L. It has to be less than or equal to 0.9. So if you have an outstanding leg, the most U you can have, the highest U that's possible is 0.9. What does U do? What is it all about? It's reducing your net area, isn't it? It's reducing your net area. Now, if all your plates are connected, you can use a U of 1. Okay? Okay. Now, real quick, I want to do physical something or other. Jacob, why don't you come up and help me for a second? A lot of you in this class have seen this. For those that haven't, then this will be your first time. So I have a piece out of a box, right? And I've got something that's a full end. Then I've got something that's an open end. And you can make one of these for yourself if you want. Okay? And this open end is where we're going to place our fingers to simulate bolts. And the closed end is where I'm going to pull to simulate load. You with me? So on this cross section, the load is uniform here, right? And the load may or may not be uniform here depending on what's going on. Okay? So you be my bolt. Got to make sure. Oh, you're not in cyberspace. Now you are. So put your bolt there on the side there. Maybe put 2 bolts on there for me. I'm going to pull with the load. Don't break it. This is expensive. Okay? And then, take one of your fingers off and poke it. Poke it. And you see over here, look how flimsy it is. Poke, poke, poke. Oh, let's go to... Look how flimsy it is. Because there's very little stress there. And look how stiff it is up here. Because there's lots of stress here, right? Now let's put your hands on both sides. It's stiff. Why? There's lots of stress on both sides. Thank you, Jacob. Let's give him a round of applause. We'll see how that turned out, right? This means that we have to include this U term in our A sub E calculations if we would expect a non-uniform stress distribution. When do we expect a non-uniform stress distribution? When there's an outstanding leg. That's right. An outstanding answer for an outstanding leg, right? If we would expect a non-uniform stress distribution, if there is a uniform stress distribution, all components of one connector is attached to the other connector, then we use a U equal to 1. Okay, so we're going to do this together. We're going to look at this connection. I'm going to ask 2 questions. Is there shear lag? And then what's the U? So the first question. Is there shear lag on this one? No. What's the U? 1. Same question. Is there shear lag? Yes. What's the U? 1 minus x bar over L. Hey, what's L? What does it mean? Distance between the bolts. That's right. What's x bar? What's that? Yeah, be careful. Be very careful. Be very careful because I love to use legs that are not equal lengths. So when you're looking in your manual, just because there's x bar in the equation does not mean you use x bar out of the manual. You have to think about what your problem is. Yes, we'll do lots of thinking in this class. All right? Okay. That's actually the best advice I could give you is don't write immediately. Think immediately. Could you use 0.6? Is that what you're saying? Well, you'd have to go back and look. You'd have to look and see if you meet the requirements. 0.6 does seem to be the low, right? However, if you're doing this a lot and you're overly conservative a lot, you run the high risk of being sued. Okay? And in this class, I'm going to expect you to work it correctly. I'm going to expect you to use this equation, and if you're not going to use that equation, then you need to tell me and reference what section, and you better be right. Okay? You better be right. You're with me. But you can use the larger. Okay? Okay. Okay, how about this one? Is there shear lag? Yes. What are we going to use? 1 minus x bar over L, right? Boy, you guys are smart. Okay. How about this? Shear lag? Why not? Because it's all, well, there's an outstanding link. No, there isn't any outstanding links. They're all connected. Right? So no shear lag, so we're going to use the u equal to 1. Great. Any questions? I hand out the next set of notes. I hope you realize that I am lulling you into a false sense of security. You're like, yeah, I've seen this before. This is going to be easy. And I'm going to give you the homework and you're like, oh my God, what is going on here? That's how the class is designed, all right? Ask questions. Don't wait till the night before to do the homework. I'll say it again. Don't wait till the night before to do the homework. Please. Okay. Block shear. Who has not seen block shear? Anybody? Everyone's seen it. Great. Well, then I will go through it at rapid speed. Block shear failure mode. At a connection, the path of least resistance may not always be controlled by A sub B. In this type of fracture, it may not always be straight across. Okay? Sometimes what may be going on, nature will want to fracture or yield on one face and then simultaneously fracture and yield on the other face. And this is really odd, all right? It's really odd, and then we're going to show some really cool videos of it in just a second, all right? But it is weird, and it is hard for sometimes for people to get in their brain and how it works. But may not always be straight across, may not always be A sub E, a failure path involving tension on one face, and shear on a perpendicular plane may be more critical. Okay, so for example, I show an example here, and I show that, hey, we have a tension plane, we have a shear plane, we may get shear and tension type failure simultaneously. Okay, and it could be a weld, and here's where the tensions are going to be, and this is where the shears are going to be. Okay, and the same things can happen in welds. It'll actually unzip in the metal around it, or it can actually unzip in the metal here. Which one controls? What do you think? The thinner one, right? Whichever one is thinner. One easy way to get around this is to make your gusset plate the same thickness as your member coming in, and you don't have to worry about it. In really, really big connections, or connections you're going to do over and over and over again, it is worth the time to do the math to see what the to not make them the same size, right? To maybe try to thin one up if you can. Depends. Okay? That's for you to decide. All right? That's for you to decide. And we have connections that look something like this, and believe it or not, this is a super fun one, because not only do we have a block shear possibility, but we also have a shear lag possibility. See that? That T there? Right? We're not going to be talking about using block shear. Well, yeah, we are actually. I'll get to that in a second. We'll have tension and we're going to have shear simultaneously on the cross section. You with me? Yeah? Great. The fracture phenomenon with tension on one face and simultaneously shear on the perpendicular face is called block shear. Once an actual fracture or yield occurs on one plane, the entire force is transferred to the other plane. What I'm trying to say here is that once stiffness is lost in one area, the load's going to try to find a way to survive, right? The structure's going to try to find a way to survive, right? And if it can, it will find another plane, right? So what's going on here is we're saying that it may fail locally here first. It doesn't want to die, though. But then all the other loads transferred over here for as long as it possibly can until this reaches its limit state. Okay? Okay. Comparison with test results show that a model based on yield or fracture on one plane and the subsequent failure on the other plane gives good results. And what we're going to find I talk way more about this in the undergrad class than I do the graduate class, but we're going to find out that there's either one or two things happen. You either have tension fracture that happens first, there starts to be a split on that front face, and then you have shear fracture, okay, on the other face, right? Or we have something called shear yielding, shear yielding along this face, and then we all ultimately have tension fracture. Now, what people love to say is that, okay, I get this one, fracture and fracture, that makes sense. Okay, but how does this yield and fracture work out? Well, remember, this is what we call case 1, and case 1 typically controls more than case 2 does. However, there are phenomenon when, if that shear plane is long enough, that all it takes is the yielding. Because when things yield, what happens to stiffness? It's nothing, right? It's nothing. So if there's no more stiffness up here, then that means all the load has to be taken by this, right? So when all additional load has to be taken by that. So if all additional load is taken by this, and then this fractures, they don't allow you to go ahead and take into account the fracture capacity of that shear. It just happens so quick, okay? Fracture, fracture. Okay? And the test data makes it match. Test data predicts it really nicely. So we get this shear yielding, and then we ultimately get this tension fracture, which would go to failure. The plane with the larger fracture strength ends up controlling. And you know what? I know this is crazy and everything, and I swear to you I'm telling you the truth, but even if you don't believe me, let's watch a video. Go to page 1, block shear. I believe it's this one is the one we want. Nope, that's not the one we want. That one did not fail exactly right because of the hydraulics. Let me get the other one here. Block this one. That's the one I meant to show. Okay. Again, we'll let it run all the way through, then I'll show it again. See, it's starting to yield, and it fails. Let's show this again. They start pulling. Okay, I paused it. I see it start to pinch. Right? See it starts to pinch. I see it start to pinch here. But notice, who cares if it yields? It's not like it's really changing the length of our member. But as it keeps going. Okay, I'm pausing it. It's fractured now. Everyone see the fracture? Hasn't fractured here yet, though. See that? Okay? It's very unhappy, all right? But it hasn't fractured yet. Okay? So I'm going to keep it going. There, it's unzipped. See, it's unzipped to there. And look, it still hasn't fractured all the way through. But now it has. Makes sense? You believe me now. Oh, yay. Okay. So in that case, we just looked at it was the tension fracture and then the simultaneously shear fracture that happened after that. All right? So that's cool and all and fun, but we like math. At least we seem to like math in this class. Okay? So how do we determine the block shear capacity? And then if you go and look in the AISC code, it gives you this big old this big old thing, man. It's just massive. Okay? And this case is this equation is the purest way, if you're a robot, to work the problem. Okay? But I don't like to train robots. I like to train humans, okay, that understand what they're doing. All right? And first we're going to talk about how to work the problem if something like call this U sub BS factor is equal to 1. Okay? And in past classes you've had with me, or past classes you've had, the UBS factor probably was equal to 1. It is no longer that lucky in this class. Okay? It may be equal to 0.5. That's all it is. It's either 1 or it's 0.5. And we'll talk about that in a second. Okay? About why that is. But if we're working these problems, I'm going to give you a very mechanical way to work the problem where you can actually understand what it is you're doing. Yay. We're going to calculate something called AGV, ANV, and ANT. This is just the gross area in shear. Well, that's here to here, isn't it? And if it's gross, what's that mean? It's yucky looking. It means there's no holes, right? Net area in shear, it means I take out the area of the holes. Net area in tension means I take out the areas of the holes in tension. I have a phi factor of 0.75. We're not going to worry about UBS, and what we're going to do is we're going to work out this inequality. Okay? You're going to calculate 0.6 Fy AGV, and you're going to compare it to 0.6 Fu ANV. And if this is lower, you have case 1 where you have shear yield tension fracture. If this is higher, then you're going to have shear fracture, tension fracture. You with me? Great. That was obvious. Almost 90% of you have seen that previously. Okay? Now, let's talk about when UBS is not equal to 1. Okay. We talked about shear lag. We talked about not being a constant stress on our cross section. That means we got 5 minutes left. We got not having a constant stress on our cross section. In circumstances like this, well, people are arguing right now about how to put some kind of U-term into these type of connections. Because there's two sides of the story. There's one side that says, oh my gosh, my computer model shows that this is bad. That this equation without a U in there is unsafe. We need to change it because my computer model says it's important. Okay? And then there's the practitioners that said, whoa, we've been designing connections this way for a long period of time, and we are not having failures all over the place. Okay? There are some assumptions that go into this, and this is a conservative model to begin with. Do we need to make it more conservative? Okay? So people have shown them enough that in the case when I have a simply supported beam with multiple rows of bolts, they've convinced the practitioners that they need to put an extra safety factor there. Simply supported beam, multiple rows of bolts in shear. Okay? Most simply supported beams are going to have shear, right? Some simple connection. They are going to have shear. So anytime you have a situation like this, you're going to need a U equal to 0.5. What? What do you mean 0.5? Shouldn't it be, are you really only going to give it 50% of the capacity? Well, that's what they're saying right now. Okay? That's what they're saying right now. And the thought is that when you go ahead and look at this failure plane, let's say it looks something like this, the thought is that you cannot take this entire A net area into account. Think about if it fails that way. You once this thing starts to go, there's no way you're going to be able to engage that entire net area before the whole thing is going to go. That makes sense, doesn't it? It does to me. But is 0.5 the number you put on it? We don't know. Okay? We don't know. Hopefully they'll agree, okay? Because they're fighting concrete every day, right? That's the enemy out there, right? Timber and concrete, right? So, we are going to have a U equal to 0.5, and sadly, this is important, sadly, when U is equal to 0.5, these simplifications don't work anymore. They don't work anymore. You can still calculate all these numbers. That's great. But now you have to do a pure plug into the inequality. Now you have to become a robot. And plug and chug. And see which one wins. Any questions on that? Okay, there are a few design examples. I'm not going to go through them. You know what? On next time we'll talk briefly about this one. That would be a good thing for you guys to look at on your own. There's way more design examples, all kinds of fun stuff. Weird block shear on a diagonal, block shear with a W shape, and then we'll talk about bolts next time. Take care.